Hi. Today, I'm here to talk about how we've built an AI engineering function at my company, Incident.io, and discuss the tools and processes we've had to create to get us there. But first, who am I, other than a person who has terrible taste in food? I'm Lawrence. I work as a product engineer at Incident.io. We build an incident response product used by companies like Netflix, Etsy, Skyscanner, Vercel, and actually plenty of you in the room. So what do? Well, we page you when things are going wrong. We help coordinate your incident response and communicate with your customers as the incident goes on through things like status pages and other tools. So you might be thinking, like, where does AI fit into this? And, well, that is a good question. And I want to kind of communicate to you that we don't just want to help people respond to incidents, but the goal for us is to actually fully automate the incident response process. We want to take a bunch of tiring, distracting, burnout-inducing incident workload away from our customers so that they can do what they do best, which is building their product. So we've actually been building this thing for the last 18 months, which is an automated incident investigation and resolution system. You can kind of see some screenshots here, where we've tried diagnosing the incident, looking at logs, metrics, telemetry, and then you can see the chatbot where responders can interact with our investigation and figure out what's going on. While, obviously this looks like quite a lot, we have a ton more that we want to build, but even so, getting to the place that we're at today has been really extremely challenging. We've had to bootstrap a new function at Incident, kind of analogous to back-end and front-end engineering, which I think the industry is gradually coming to term AI engineering. So to give people an intro into what AI engineering actually is, I think it's fair to say that every product today would probably be built differently if you started from scratch with AI tools. But not all products are going to demand the same level of AI sophistication. So we've invented this kind of spectrum of AI sophistication at Incident, where you start with no AI. So this is where every company was maybe 5 years ago, where you have no generative AI inside your code base. And when you start, you kind of look at existing product features and you go, how can generative AI help us improve them? And you add small one-off kind of extensions to your existing product experiences. Things like summarization, where you're going to an LLM, you give it your data, you ask it to execute a prompt, you get the result, and you pass it straight back into the product. But it's pretty simple. You're just going into one LLM, and it's just a kind of fire and forget call. And this is where most companies stop. And there's a reason for that, and it's like most companies don't need the level of sophistication that comes next, which is where you start entering the territory of what I would like to term AI engineering, which is where instead of it being a fire and forget into an LLM, you go into an LLM, and then you go back into more LLMs. And we'll talk about this in a moment, but this is where the complexity really ramps up. Now, it would be remiss of me not to say there is another, obviously, level on this, which is foundational model engineering. If you're working at a company like Anthropic or OpenAI, this is what you're doing. You're building the models that everyone else uses. That is not what this talk is about. It's not what people normally use when they use the term AI engineering. So there you go. You've got your grounding now. But what is it about AI engineering that means the complexity just hikes up? Well, I want you to have a look at this diagram here. So in this, we're receiving some data from our application. It's going into an LLM, and then what the LLM spits out can optionally go back into other LLMs and into this cycle where you call prompts repeatedly, one after another. What I want you to realize is that every LLM prompt is a non-deterministic function. And when you start wiring them together, you compound the error, you compound the unpredictability of this system, and you produce something that has a lot of emergent complexity. It's so complex, in fact, that it's worth nouning, which is why I think the AI engineering term is worth talking about. And it's because you need totally different tools and processes to deal with this type of engineering. In fact, actually, we borrow a lot of things from ML and other disciplines in order to manage it. So at Incident, we've been forced to manage this, and we've been forced to learn it, both from the bot that we've gone and produced, but also from our investigation system. And that's mostly because if you look at the example of an investigation over here on the right, that summary that tried debugging what was going on in the incident had about 109 LLM calls, or 107, got that wrong. Obviously, at this point, when a single investigation can run into hundreds of LLM calls, you're kind of at a crazy amount of complexity there. This is the nightmare scenario for anyone trying to have a simple system that doesn't keep them up at night, which is ironic given what this is trying to achieve. But anyway, I think that's all doom and gloom and why AI engineering is hard, but I do have some good news. So if I look back over the last 18 months of development, we went from building very, very simple AI features to building something much more complex. And I think there's been clear phases of maturity in that timeline that have allowed us to gradually increase the level of sophistication of how we're using AI technologies to build much more compelling product features for our customers. So these are development, which is the initial stage of adopting generative AI, which is where you just want to build something with generative AI, so just like call a prompt, right? But then once you built it, you're putting it in production, and that is a whole different thing. Like your customers are experiencing it for the first time. You aren't the person using it yourself necessarily. There's a ton of other problems that occur here. And then the third phase, which is once you've got something that seems to be working, you want to evolve it. Maybe you want to improve it. You want to do that without causing regressions, and that turns out to be really, really hard. So I've got to put these in a diagram, which looks like this. So as we progressed through these phases, we've had to invent tools and processes that have helped us manage the complexity and solve the problems that we found at each different phase. So we built a lot of these tools ourselves, and we built them into our product, actually. So they're like internal tools grafted onto our normal product experience. That might not be how you would like to work, and importantly, that doesn't really matter because, one, there is a ton of open source tools that can help provide a lot of the functionality that I'm about to show you here. But also, these problems and the solutions are kind of generic to any AI engineering team. So if you're doing this type of work, you can look at this as a case study in how you might solve it, not necessarily you must do it like this. So for the rest of my talk, I'm going to walk you through each one of these phases. I'm going to show you some of the problems that you hit at each one of the phases, and then I'm going to discuss how we solve them. So yeah, let's get going. Cool. So you start at development, and remember, this is starting from you have no generative AI in your code base at all. There are a couple of problems that you hit immediately. First, like, how the hell do you even call an LLM? Like, this sounds really simple nowadays, but like, what interfaces do you use? How do you send it your data? How do you parse the data that comes from the LLM back into your system? So the first thing that we built, and is where I would recommend that anyone doing this starts, is an abstraction around the concept of a prompt. So you can see this as an LLM-powered function that receives some arguments, so data rendered from your app, and it receives a result back from the LLM that it can pass back into a type that it expects. So when you're doing this, and when you're building this prompt abstraction, you want to make sure that if you have one, you leverage your type system. So certain providers, such as OpenAI, they support things like structured output, which guarantee that you get back a result that matches a JSON schema that you pass when you pass it your request. If you have a type system that can do it, you should probably investigate converting from your types into a JSON schema so that you can call these LLM prompts in a very like language native type of way. Second is make sure that you are multi-provider compatible. Like we have clear evidence in our system that Sonnet can be a lot smarter than GPT 4.1 in certain situations. But also GPT 4.1 is a much better balance of price and performance for most of our workloads, and is why we actually use it for most of our stuff. So I guess like the key learning here is don't lock yourself out, and this is the abstraction where you support that multi-provider setup. And this is also where you add instrumentation, which just trust me, you're going to want to add like token usage, cost, anything that you want to add here. Just put everything into this layer because this is going to be the utility that you use to interact with large language models. In our monolith, a prompt looks like this. Sorry, that might be a bit small, but actually all you need is really the shape of this thing. So you've got a single file, and it implements a prompt interface that the rest of the code base understands. It defines its input, so this is the data you're going to be sending into the prompt. It provides its result type, which is what you're expecting to parse back, and methods that you use to build the prompt messages that you send off to your provider, which should be familiar to anyone in the room who has been building this stuff. Things about this, it's really simple. It's super easy to copy and paste, which is useful because you're going to be building a lot of these prompts. And it also means that you have a familiar structure whenever you go around your code base and all your prompts look the same. But once you've had this, you're going to hit another problem, which is how the hell do you go from a prompt that you've gone and built to testing that it actually works for some set of outputs? Like, how do you even get a feel for how this thing functions? The problem with prompt engineering, as lots of you will have realized by now, is that it's very easy to make small, innocuous changes to the prompt that you think won't impact how it behaves, but actually cripple it for some really important use case. And unlike traditional code, if you run a prompt with the same input, you will get different results each time. So you can't even trust that you would run it again and see the same type of wonky behavior that you saw before. And this is why it's really important and well, important and challenging that you find a way to unit test your prompts. And you're going to need a new type of test for that. So you've probably heard about these. So evals, at least in our system, are LLM unit tests. Each unit test, or each test case in an eval suite, is a tuple of prompt input, so stuff you will render into the prompt, and some expected output. The eval suite itself then defines some matches that tell you how to go from what the prompt returned for that given input, the expected output, and whether or not you actually pass the test. So in our code, evals are coupled directly to prompts. And again, possibly a bit too small. Sorry, guys. What we actually end up doing is our prompts themselves implement an eval method, where we say in the eval method exactly what kind of matches we care about for our eval suite. So this prompt is kind of a contrived example, or at least I don't think anyone has this in their code base. It will convert normal human English into pirate speak. So it will try and convert things into "yeah" and other things. So the things that we care about in our eval suite is, does the output actually look piratey? So have we actually produced something that looks like a pirate would say it? You could do a traditional test and just look for like the word "yeah," and I guess that would work, I guess, if all of your output includes "yeah," maybe that's good. But actually, it's really useful in evals to use other LLMs to be testing the output of your prompts. And that's what we do here. So we have a lot of helpers that help us use LLMs as a judge in order to power our evals. We also use LLMs to confirm that the meaning of the text doesn't actually change. But we can mix these up with our standard Go test frameworks in order to run tests like, is the output empty, and ensure that like normal behavior comes out inside of your app. So these prompts are in one Go file, and the eval case is in the YAML file next door. And we can run these evals from within the code base, so developers can run these locally, test changes in their prompt, run against their eval suite, see if anything changed, and then add tests if they need to. And this is how you write prompts and get the confidence that it works with your expected data. We also run these in CI so that we can catch regressions before they make their way to production. If you go and change something and you go break a load of prompts, you're going to want to know before you deploy it. This does require thinking about caching, so in order not to break the bank, you can grab me afterwards to talk about the specifics if you're trying to do this. Cool. So now you have a prompt abstraction, and you have your evals. So you're set to build a ton of AI features at this point. In fact, most companies who are doing the AI sprinkles can kind of stop here. I think those are pretty decent tools, and you're pretty set up. It's the complex apps that need more, that need to go further than this. So complex apps, they struggle when you put them in production, and your customers start using them. And I want to share some examples from our app so that I can illustrate some of those problems and some of the solutions that we've implemented. So what we have here, like I mentioned it before, we do our investigation, but then we allow you to interact with the investigation through a chatbot. So this chatbot's like fairly complicated. It can do a ton of different things when you speak with it. And what we've done is we've characterized in this system that an AI interaction is a message exchange that you have with the chatbot. So for any AI system, whenever you want to start understanding it, scoring it, grading it, you need to define what its unit of interaction is. So in this case, it will be a message exchange. And then you need to make it easy to debug each individual interaction and also debug them in aggregate. So if you have a look here, here's a real example of an interaction from our account. And you can see a bunch of diagnostic information we've stamped in the footer, which can be really useful and help people debug things. But the real thing is when you click the evals button, this is where it gets interesting. So when you click evals, you're booted into our internal dashboard, which helps you with a ton of different diagnostic information. And now you can kind of just see the expanse of this. I'm going to go into each part of it in more detail in a moment. I think there's lots on the screen, and I want to explain it by describing the problems that we're trying to solve with each different piece rather than going through it from the UI that we've got there. So the first problem that you have is that LLMs are non-deterministic. We've mentioned this. You can't replay them and get the same thing back. So in any of these systems, if you want to truly understand what happened and debug things, you need to be storing everything that you actually put into the LLM and everything that you get back. And then you need to expose this to someone so that they can actually see the data and debug it if things go wrong. So we expose this in what we call a trace view. Now, AI traces are a bit different from your standard observability traces. They have richer context. They have all the data that you sent in. They have everything that you got back. They also have model parameters, such as temperature and which model you actually use. That's really important. You want to expose this in a UI. because you also want to expose the ability for you to rerun interactions so that you can go, this thing went wrong. I want to see what happens if I run it 10 times. Was it just 1 in 10 times that it goes wrong, or was it all of them? And you also may even want to try different models. You also will want to go from an AI interaction that you've seen in production, where it went wrong, and you want to steal that as an eval and put it inside of your code base as a regression test. And you want to make that flow really easy so that you can quite flexibly tweak the prompt to account for any poor interactions that you find in production. So I'm going to show you what this looks like in our system. So here is the first kind of inspect view. So this is us looking at a span. This represents a single call into an LLM and all the data that we sent it and all the data that we got back. So there's a couple of things here that are quite useful from an AI engineering perspective. First, you see the response. That tells you what you actually received back from the model. Obviously, that's useful. You also get the model that was used, and then you see the input and output tokens. Super useful for cost management and latency debugging and just general debugging, actually. But then also you have the full prompt below. So there's a lot of prompt issues that you can hit if you ever get the formatting of your rendering prompt wrong. If, for example, you poorly format your markdown and then the headers are totally out of whack, the LLM will probably interpret your document in a very different way than you would expect it to, and that can cause really poor problems in your system that are almost impossible to see in your rendering logic, but really easy to see if you as a human eyeball the whole of the system prompt. So yeah, that's the inspect view. We also want to let you rerun your prompts and compare to other models. Honestly, the best thing about this is that it's by rerunning against other models that you develop an intuition about how these models work and which things are strong and for what reason. I know, for example, that Claude models are much better at understanding OAuth. I hate that I know that, but it's very useful when you have to debug that. Cool. And then I mentioned this before, but stealing an eval, so going from a poor interaction in production and pulling it down into your local eval suite so that you can tweak the prompt and experiment, that's super important. And you can see here we just offer people a command so that they can copy it and bring it down into their code base, which helps track regressions and fix them. Cool. So like prompt evals, you will then want to go from, are your prompts working, to, is my interaction actually good? And defining whether or not an interaction has been good or bad is kind of a hard question. Interactions can have a mix of prompts and a mix of code. They kind of combine together to produce something much more complex to grade. So we need to be able to score kind of these arbitrary interactions and determine if they're good or bad. And what we use for these are scorecards. So I've got the original chatbot interaction up on the top left. And what you can see down on the bottom right is what we call a scorecard. So scorecards run graders against any generic AI interaction inside of the code base. And they end up producing metrics that go, hey, like the alignment was this, and give you a numeric value. And I want to dig into alignment for a second, because it's an example of how you can score this. So like alignment for us is, did the bot do what it was asked to do? This is actually kind of like more complicated than you might think it is. You imagine if you get given a request to a chatbot and your LLM decides to do a certain action. If you use the same LLM to come along and grade it and go, did you do the right thing? It might reasonably deduce that it should do exactly the same thing that it did wrong last time, because like it's the same model, right? That's all the same information. So I want to give you a trick if you're ever building these scorers, which is you should leverage time, and you should grade and score your interactions probably about an hour after they happen, so that when you grade them, you can use everything that happened after the interaction closed to determine whether or not they went right or bad. Customers tend not to poo emoji respond to your messages if you did the right thing. If you can include that in your scoring process, then you end up with really reliable scorecards, and suddenly you have this like functionality that for the first time in all of these systems gives you an objective definition of what is good for your AI interactions, and we can use it to build a ton of other tools. So an example would be this. So every feature that we ship that is an AI feature, we give it a pulse channel. So whenever we end up creating a scorecard for those interactions, we will post that scorecard into the pulse channel with the good, the bad, and the ugly. All the engineers working on these features are subscribed to these channels. When they start becoming too noisy, we end up with a Copilot interactions bad pulse channel, where we just send the bad interactions. And it's through looking at these that you build an intuition about where your system is weaker and how you would go about improving it if you ever get a chance to do so, which hopefully we're all in the game of doing here. Great. So That helps you run in production, and it helps you know that customers are getting value. The final phase is about making changes when the system is already working, and this is arguably the most complex. So few companies have cracked this. Even big names have some serious regressions in their AI products that you only notice through people suddenly going, hey, like, this model is rubbish. I swear last week it was fine. And that's because it's really difficult to make a change and know how it's impacted the system for real customers. And you need to be able to do this fast, as it limits your iterations on improving the product. And if you can do it reliably, you can experiment faster, which allows you to out-execute your competition and hopefully build a better product. But doing this requires you to combine together a few concepts. So what we built is this concept of backtests. So this allows you to rerun a bunch of AI interactions against a known data set of resources. These backtests produce an aggregate scorecard. So each interaction gets its own scorecard, and then we can aggregate scorecards together to see over all these interactions, how did we do, with a ton of like digging tools to get at the underlying data and narrow it down to all these bad interactions had this type of quality to them. For investigations, where we're trying to debug our incidents, we'll run the investigation engine against historic incidents. And that lets us tell whether or not our change has made things better or worse, and if it has, where it went well and where it went badly. So I'm going to use an example of one of our developers, Millie, who's making full use of these tools. So this is Millie doing what she does best, which is finding subtle and significant bugs in complex code, often the ones that I wrote. And it turns out that in the investigation system, we were passing some code changes down to our shortlist because we thought that they were high-confidence code changes. And they were high-confidence code changes, but we were highly confident that they were unrelated to the incident. So that was not smart. Millie found this, so she's gone and made the change. She deploys it under a feature flag. And then she ends up running a backtest. And we already have a code change database, so incidents that were caused by code changes. And we can run backtests against our dataset whenever we want. And she's able to, within maybe 5 or 10 minutes, get an aggregated scorecard of all 29 incidents in that backtest. And it says there on the recall score, which is how many of the code changes that actually caused these incidents did we manage to find, that we've had a 15% improvement in recall. And that's really massive for us. That's big. So I think with these tools, you can see we've gone from it being such a complex system that you can't really touch it and know how your change would impact it, to just a few hours to make a change, deploy it, test it, build confidence. And Millie can even identify that it's going to reduce the costs because it's so obvious when you're looking at the scorecard. And she can also tell you why, because it exposes that information too. And that's the confidence you really need for these systems. Which means that we have one final problem left, which is Millie did a great job, but how does she celebrate it? Engineers, it turns out, are naturally competitive. And if you want, you can turn this like getting a high score into a bit of a game, and they'll enjoy it, and your team will feel very motivated. And you'll also get the benefit of being able to track your baselines at a continual level on each one of your games, where a game in this case is how good are you at the game of finding what code changes cause this incident. So for this, we created a really basic leaderboard. And this is working really well for the way that we work nowadays, which is we've adopted an ML pattern of this build your evaluation criteria, which for us are scorecards and graders. Then you want to establish a baseline. So you run a backtest, which tells you how good you are against those evaluation criteria. And then you do hill climbing. So you give this to an engineer and you go, you have a week or you have 2 weeks. Just pick a metric on there and just make it better. Tell me what you learn, and then see if you can make one better without making everything else worse. And then what you do is you get a leaderboard so that when one of your engineers wins, they can go stick their scorecard to the leaderboard, and then their face is against the investigation code changes, causing code changes, and Millie sat there as the person who last won that challenge. It just brings a bit of the fun back. That's it. That's a speed run of the tools and processes from the last 18 months that we've been working on these systems. It is a lot, but adapting this can make working with AI actually manageable, even for very complex systems. With this, you can actually build systems reliably, especially complex AI systems without serious regressions, which I think is actually something very few companies can claim to do right now. I know we spent a lot of time on the tools, but hopefully you can see that they solve for some very real human problems. For people on this journey, it's worth remembering that non-deterministic systems suck. There is a reason that distributed system problems are hard and that SREs are so grumpy. This and other aspects makes working with AI a roller coaster. So you want to pick tools that can bring objectivity back into your system and make sure that you actually stabilize the team with these lifeboats in the form of scorecards, graders, all of that lot. And finally, when the wins come, however small, make sure that you're celebrating them. They are probably hard-won. I will finish with this, which is, if this sounds interesting, I cannot shout loudly enough. We are hiring product engineers in London right now to come and work on these systems. We have just raised $62 million to hire people like you that can help us build these systems. We want you to come join us and help build, push the boundaries of what AI can do for incident response. It's worth saying as well, you do not need existing AI experience. We're hiring product engineers to come learn this stuff and learn it with us. None of us have this in the team either. There's a site that we have dedicated to all of our building with AI resources. Tons of technical posts on there, really useful if you're getting going with generative AI tools. If you have any questions on this talk, you can LinkedIn me, email me, whatever you want to do. Just tap me on the back. I'll be at the booth tomorrow. So yeah, that's it. Thank you.